we used yesterday. And if I gave this to you on your test, I would give you this entire explanation so that you have what every single variable and term means. But if you notice, e to the kt is part of that equation. So this is 409, page 2. All right, so here is where, if you're a chef or you're a restaurant, you want your food to go out at a certain temperature, right? So that it's not going to scald people, but it's also not going to be cold. So knowing how quickly food cools is important. Or if you need to chill something in the refrigerator, it's going to cool at a different rate in the refrigerator, right? So Danny boiled water for tea after waiting for 3 minutes. Danny found the temperature of the tea to be 60 degrees Celsius. He likes his tea at 40 degrees. So how long should he wait before drinking his tea? Maybe on Monday, we could actually boil water in my kettle and just see how quickly it cools in the room and see if it actually does cool using Newton's law. Boil water, Newton's law, experiment Monday. That'd be kind of interesting because I've never actually done it to see if, we make our prediction and then after 20 minutes we see if the temperature is what we predicted, All right, so can someone tell me what temperature Celsius water boils at? 100. This would also work for Fahrenheit. Just in this situation, all of our information needs to be consistent in Celsius. So as long as all of the temperatures are in Fahrenheit, you can also use this for Fahrenheit. So our first step is to calculate K for this cooling situation. So it says U of T is the temperature after so many minutes. Capital T is the surrounding room temperature. U sub 0 is the starting temperature. That's the boiling water. And then little t is your time. So the way we're going to set it up is after 3 minutes, it's 60 degrees. So 60 is the current temperature of the tea. That goes on the left. The room temperature, it says, is 21 degrees Celsius. So that's big T in this equation. So then I write plus parentheses the starting temperature, which was 100, minus the room temperature again. So there's two big T's in the equation. So I'm seeing 21 written twice. E to the K times 3 minutes. So the only variable that I don't know is K. So all of this is going to allow me to solve for K. What's the rate of the cooling? So let's do order of operations correctly here. I first do parentheses, right? So 100 minus 21, is that 79? Okay, but 79 is linked to the E. So I can't add 21 plus 79 because this is multiplication over here. So my next step would be to subtract 21 to the other side of the equation, right, to get rid of it. So that would be 39, right? So 39 equals 79e to the k times 3. See how we're going to have to use logs just like we did yesterday to solve this equation? All right, so I divide both sides by 79. I'm just going to leave that as 39/79. So I have 39/79 equals e to the k times 3. So if I'm stuck in exponential form, I have to rewrite this as a log. So what's the base of my log? And what's the rest of the equation? So rewriting this in log form. So it'd be log base e, right? So that's the natural log of e of 39/79 equals k times 3. So I can take this natural log, just use the ln key on your calculator, divide by 3 at the end and find k. So I'm doing the natural log of 39 divided by 79 in parentheses, hit enter, and then divide by 3. So k should come out to a negative decimal. So what does someone get for k? What is it? Negative 0.235. All right, I didn't quite finish this problem, but I ran out of room here. So K is the constant that I want to use to answer the rest of this problem. So the problem says, what? We want to know if he likes his tea at 40 degrees, how long should he now wait? So the current temperature of the tea is what? 60. It already cooled to 60. So how much longer should he wait? He wants the tea to get to 40, right? So I'm going to solve 40 equals 21 plus. So 60 is what I'm starting at. Whoops. I'm starting at 60. I want to cool to 40. And then e to the negative 0.235 lowercase t. So you're going to basically do the same process we just did, solving for little t this time instead of solving for k. So see if you can correctly do the order of operations, just like we did to solve for k, to solve for t. So actually thinking about what just happened, it went from 100 degrees down to 60, right? Isn't that, it just reduced itself by 40%, right? So then it went from 60 to 40. Isn't that about the same reduction? 40 out of 60 is 2/3. 60 out of 100 is 60%. So it's yeah, I mean, very similar amount of time because it went from 100 down to 60 and then 60 down to 40. Thinking of half-lives, right? It reduced about the same amount of time. So now let's do one more Newton's law. So now on number 4 on the next page, this is now a pizza. So you can do it for objects cooling as well as liquids cooling. This time it's all in Fahrenheit, so you can use the equation, but all of your numbers are now in Fahrenheit. So it says the pizza is baked at 450 degrees. So we're going to say that that's the starting temperature of the pizza. I don't know if that's completely accurate. I don't think your pizza is the temperature of your oven, but it starts at 450. We're going to say it cools to 300, and you want the pizza to reach a temperature of 135 to be comfortable for eating. And the room temperature is 70 degrees. So it says it's removed at 5 p.m. After 5 minutes, it's 300 degrees, right? So can you figure out where to put the 450, the 5 minutes, 70-degree room temperature, and 300 degrees? So you need those 4 pieces of information to solve for K first. Once you have K, they would like you to figure out how long it gets to 135. Which one are you on? This first step with the K? Oh, I think this is the second equation, right? 135 is what you want. It's currently at the 300. And then I put the K value in here. Did you do it from 450? So you must have gotten, if I got 12.6 minutes, you would have gotten 17.6 minutes if you did it from the starting value, because it would just be 5 extra minutes. Did you get 17.6? Oh, then you did it right. You just did it from the 450. So that's fine, because either way, if the time was 5 p.m., we would have had 5:17 p.m., right? I was just starting from 5:05 and you were starting from 5. Yeah. All right, so that's Newton's law. So we'll do it maybe